So someone found my YouTube video about it on my channel and just like it opened their eyes. And then they confronted the person and they invited me for part of it, which it's I don't know, it wasn't much, but I was interested in it and taught the kid how to report it because at the end of the day, the catfish is stealing the identity of other women and is using their pictures and they sent some naked pictures of someone that didn't belong to them. So that in and of itself is a crime.
Wow.
So I taught them how to report it to the authorities and how to report it to the FBI. It's my understanding that's what they're doing right now. It just took them a little bit.
Yeah, but I don't think the FBI is going to do anything. The
Sometimes
FBI.
they find the victims and they inform the victims. Even if they don't prosecute like the perpetrators, sometimes it's just about getting information to the victims, especially when this has been going on for years.
Once I had a beautiful chick match me. I don't remember somewhere. And then we started talking, and I didn't suspect anything. And then at one point she says, "I need to make sure that you're real. Please hold up one finger, hold up two fingers, take a picture of yourself." And I don't remember how I was able to get her email, and the email was obviously a guy's name. I don't
Yes,
rem-
this is how we found out originally about this person because they kept up their school Zoom class and it said, first of all, you could see it was the person who was posting. It had the name, Daniel Schnur, and it said, "Find me here," posted an email, posted a link, and then said, "On this social media, my name is Dan of War." We connected that to Huntress Love, which was their alias for their female account. We got all of it so quickly, just having that information.
Mhm. Yeah, but I don't think the FBI cares. I mean, the FBI is probably over.
On some level, they're overwhelmed, but on some level, it's the squeaky wheel that gets the oil. So I don't think that it does good not to report it. Especially, we found some articles to indicate this person was involved in some sort of CP raid. So they shouldn't be on the internet. The fact that
I
they're on the
don't.
internet at all is a crime.
I
The fact
don't
that they're committing fraud is
even
worse.
s- even CP. I don't think the FBI cares about CP. I don't think the FBI cares about anything. You saw they all the FBI almost got shot at and almost got the president killed. That's the FBI. The FBI are a bunch of baboons.
That's the secret. That's the Secret Service. That's
It's
not
the
the
same. I
FBI.
mean, that's supposed to be the top, the creme de la creme of the FBI. So
It's a
it's
different branch. It's a branch of the CIA, actually. Branch of police.
anyway. It doesn't matter. So the CIA is supposed to be even better than the FBI.
Yeah,
So
feds and police are not really the same thing.
anyway,
It's a
look.
more special.
Yeah, these people are absolutely useless. I wouldn't. I don't think they care about anything except for getting paid and their
I wouldn't say
pension.
they're useless, but I don't I'm not expecting mountains to move, but I'm not saying it's useless. I think that you should absolutely report it because at the end of the day, it's gonna be a robot that takes all this information, algorithmically categorizes it, and eventually alarm bells go off to tell them
No, I
who these
think
people are and how to
no.
deal with it.
I doubt it. I doubt it. These people are useless, unfortunately, or fortunately. I don't know. It's probably more fortunate than unfortunate because whatever they would do, they would probably do against us before they would do against actual criminals because that's the nature of that's the nature of government. So it's um it's a waste of time. I wouldn't bother. Like I was multiple times attacked by um, and a bunch of stuff, and I reported it, and they never contacted me. It's a complete waste of time. You go,
Did you contact like local
you go
police
to.
first?
It doesn't matter. I mean, you go. I mean, if it's online, how am I going to
That's the
contact
protocol.
the police? No.
Yeah, you contact the police and then they patch you through to the FBI.
No, you can go to the FBI website and fill out forms and submit, and they just never contact you. Done. That's it. Look,
Yeah, they
anyway,
contact you if they need additional information, which is why you should call the police
okay.
first, especially if they're
I
stalking your
mean,
address.
look. If you feel that it's worth it, then go ahead. I gave up on the on the law authorities. I don't think they're useful.
You're also not within the United States.
What?
You aren't within the United States.
I am within the United States.
No, you aren't.
What do you mean I'm not? I'm a U.S. citizen, so they should respond to.
Told me you're in a different country.
Well, I'm traveling right now, so what if I'm traveling? So because I'm traveling, I'm not entitled to the protections of the law. If I would commit a crime, they would come after me. But if somebody commits a crime against,
Yeah, but the local authorities would come after you, not the American FBI.
anyway, it's whatever. It's an interesting story, definitely, and it's good that I would just expose that person on YouTube. So if you want to show me, if you want to expose that person, I don't even know if it's a
Oh
good idea.
yeah, I'd love to show you, considering the fact that
No,
I
it's
worked hard to do
probably
that. And not only that, but I was kind of shunned from like
no.
even
I don't.
spaces for doing it.
I don't think it's a good idea because YouTube would probably come after me instead of after them.
It's
There's
on
this
YouTube anyway, so
there's a YouTuber, uh, a girl that I follow. She has the longest legs or something. She's really tall, a cute girl, and she tells the story that when she was, I think, 12, that a predator raped her, and that's it. That's the story, and nobody cares. So actual predators, no one really cares. Like if you have pictures or whatever, then yeah, they'll probably come after you. But if you actually do stuff against little people, it's most likely nothing will happen. The actual criminals get away, I think.
I think that there's definitely like an incentive to like police them more socially, especially considering you can't take these people off the internet by force, even if they've been convicted of like having child porn. If they're not in jail, you can just find a different device and get online somewhat anonymously, and people don't like immediately go police that. They might over time, they don't do it immediately. So yeah, I think that this keeps communities and keeps people safer, and especially in the case of this victim who was just a 20-year-old guy who thought that he was dating an 18-year-old girl, like this protected him. So I'm glad that I did it. But I
Yeah,
don't think that we should say ignore it and don't report it, because
I mean,
at the end of the day, they stole multiple people's identity and they're sending naked pictures of somebody else
the
claiming
question
to be
is,
that person.
can you find the persons that whose identity has been stolen?
When we tried to, we couldn't find any accounts that weren't run by Daniel.
You couldn't find
So
any
they might have left
accounts
the internet because of the identity theft. We
so-
couldn't find any accounts that were not Daniel's.
that were not Daniel's.
What?
You couldn't find any account that belonged to the person whose identity has been stolen.
No, no. When we tried to, it was all just Daniel pretending to be that person.
Mm. Did you do a reverse Google image search?
He did.
Hmm. Anyway, it's definitely interesting, and it's good that you're helping people. I'm happy. How was your life?
Pretty good. Made some fresh bread today.
Fresh bread. Wow.
Yeah, yeah. I made bread and soup.
Soup. Wow. I made eggs today, and I don't know why, but it didn't sit well in my stomach, and I feel like a little bit nauseous the whole day. I'm sort of dysfunctional.
I'm getting nauseous, but it's only like a head type of nauseous where I feel like I have like sort of the spins a lot, and my nasal passages are really clogged up, you know.
Hmm. Yeah, I can hear.
Yeah, I'm not sure. I forget when I last took my medicine. Now I'm not sure when I can take it again.
Mm.
No, that's that like nasal spray I've been using. It actually works. It's just ugh,
Do you know a person by the name of Amnesiac? Amnesiac
no.
6? So I
I've never met them.
it's like it looks like a trans person. Like I'm looking um at their profile picture. It looks like a trans person. Anyway, so this person approached me a long time ago, and like seemed interested in actually debating me. I don't remember if we actually debated on YouTube, but I'm looking at the chat. Wait, is that a message from you? Did you just receive? Because I just heard like an incoming message.
I was just
Yeah.
someone
Oh, yeah. I know that I'm
in the
sharing my
library.
Uh. Oh, Cena says I'm sharing my conversations. Yeah, yeah. I know. I'm sharing my conversations on purpose with this person. I mean, about that I had with this person. It looked like a normal person. This amnesiac person looked. Everything looked normal, and then one day this week, and during one of my streams, they came to the whiteboard and they started writing stuff about me, like nasty stuff that I had to ban them right away. Really strange. I don't understand this behavior. Anyway, so that was this week. I'm having a hard time with quantum mechanics. Do you know anything about quantum mechanics?
Hardly. No. I
Like,
watched your
mhm.
video yesterday, but it's like I don't have like a background in it, so it didn't really mean anything to me.
I don't think no. I don't think anyone has background in it. I think everyone is. No one has figured this out. This part of quantum mechanics, no one has figured out. I don't think so. So You know as much as the biggest. You know as much as Einstein. I mean, this gets to the ultimate debate between Einstein and Bohr. This is the debate about quantum mechanics, about the essence. No one knows what's going on. I don't know what's going on. So I don't know what to say. I mean, special relativity ended up being a joke. General relativity, I haven't finished the course, but I seem to understand it better than anyone else. At least the gravitational part. Like, I'm the only person basically who understands why the apple falls towards the ground, why the apple accelerates towards the ground. And then when it gets to quantum mechanics, I seem to be beginning to understand better than anyone what's going on, but I'm still uncomfortable. Like general relativity, I'm fairly comfortable. Special relativity, very comfortable. There's nothing to it. But when it comes to quantum mechanics, I'm beginning to get a hold of it, but still a bit confused. Anyway,
Yeah, well, it's complicated.
yeah.
All I know about quantum physics is like is the type of shit that's used by people who market this law of attraction stuff to people, and it comes off as like pseudoscience and just makes a bad name for like the whole thing because it comes off as like basic like saying but like you just say quantum mechanics, when you can't explain something.
That's exactly the
So I don't
problem.
know much of it. That's why. Yeah, that is the problem because now I don't know the first thing about it. All I know is a lot of like hippies and like drug addicts decided to say that was their reason for doing everything.
Exactly. And that's why I got into physics like a month ago. That's what happened. I was debating this guy. His name is Mandibles. So I was debating him about, is the universe determinate? Is the universe basically predictable? And he said, no, the universe is indeterminate and we cannot understand it. And I said that I don't I mean a universe that we cannot understand. I cannot understand such a universe. For me, the universe is understandable and it's mechanical. But he said no, quantum physics proved that it's not. So basically, people use quantum mechanics to say whatever they want to say whatever they want. It's like whatever they want to say, they can say because quantum mechanics allows them to say it. So the way I'm understanding it is that we don't understand quantum mechanics. Because we don't understand it, it ends up being self-contradictory and it gives weird results. That the universe is bizarre, the universe is weird, the universe is unpredictable, the universe is weirder than we thought that it could be, all sorts of nonsense like that. That actual physicists, that's what they say. And once you say that, then anything goes. Then if you want, there is a God. If you want, it's whatever you want. If you want the law of attraction, whatever that is, or the law of attraction, whatever you want, and basically you can abuse. People end up abusing quantum mechanics to whatever ends they, for their personal benefit. And people are abusive using quantum mechanics.
Right, yeah. People are using quantum mechanics more as like a pseudo like psychology tool than they're actually talking about
Yeah,
physics.
they use it for whatever they want. For whatever they want. It's a very, it's a very useful tool. If you want to abuse someone, then quantum mechanics allows you to abuse them. Well, quantum mechanics says whatever you want it to say. It's like the line from The Matrix. Did you see The Matrix?
Yeah, I've seen them all. What were you talking
So
about?
Morpheus says you take the blue pill and you wake up in your bed and you believe whatever you want to believe. So quantum mechanics is you wake up in your bed and you believe whatever you want to believe, and people, they believe whatever they want to believe, and you can't stop them. Anyway, I don't know what to say. I just don't know what to say. I found this channel, Shy Physics. It's a chick. She always shows her boobies,
Yes.
but she seems to be a legitimate physics girl. Here,
Nice.
she's always showing her boobies. Always, not sometimes. I don't think there is a single
It
time.
always says what is gravity. That's the first video. That's so funny.
Yo,
Hi, Mr.
Like,
Andrew. What's up?
I'm great.
That's good. So, Andrew, do you want to debate? Do you want to talk about?
what?
Do you want? Wait, he always either disconnects, turns off his headset. He's impossible to finish a sentence with, aren't you, Andrew?
Yeah,
Why do you do that?
exactly.
You always have an excuse why you have to do whatever you want to do.
Actually, I will tell you later, but maybe not now.
Okay,
I will tell you. Trust me.
okay. So do you want to talk about quantum mechanics? Do you want to talk about physics?
Yeah, sure, sure.
Okay, what's
We
your
can
question?
talk about quantum mechanics.
Okay, do you have any?
What's your topics?
What's my topic? Why don't you ask me a
Yeah,
question? What
about quantum mechanics. Like, what's your subjects?
What's my subjects?
Mm-hmm.
What do you mean? Well, I mean, I think it's not that I think. I'm assuming. I have to assume that we can understand quantum mechanics. So the way I understand it, quantum mechanics is just a wave artifact of the ether. So it should,
Ether.
yeah.
What do you mean by ether?
So ether. Let me ask you a question. Why do you think the apple when the apple falls towards the earth? Why do you think
Mm-hmm.
that happens?
Oh, so you're asking me why gravitational force do
Yes.
exist?
Yes.
Actually, I have no clue. I knew it's existing. I knew it do exist, but I have no clue why it do exist.
Okay. So you're the same as everyone else in the history of humanity, except for me.
I'm different.
You're the same. Everyone,
No, I'm different. I'm an alien. I'm from Mars.
it doesn't help. You're the same as everyone on Earth.
Sure.
Being from Mars or from Alpha Centauri doesn't help you. You are the same.
Yeah.
You're the same as everyone else except for me. I'm the only one who's different.
Oh, wait. You're the only one who's different from your
Yes.
own perspective. From your own perspective, I'm the only one who's different from my perspective.
No, you're
It's called
not.
philosophy of mind.
No, you're exactly
So
the
why are you
same.
different?
I'm different because I understand why the apple falls from the tree. And everyone else does not.
Sure. So if you gave me 20 seconds, I can answer you with why Apple fall.
I give you 21 seconds.
21. Yeah, decent.
Yeah, go ahead. Look it up. Why don't you ask
I'm not looking
Chat?
anything.
Why don't you ask ChatGPT why the apple falls from the tree?
Why?
You said give me 20 seconds. Why don't you go ask ChatGPT what ChatGPT thinks?
ChatGPT is super bad. Oh my god, doesn't even answer me. Sure. So Apple
Mm-hmm.
falls as an
Mm-hmm.
attraction
Mm-hmm.
due to it having mass. Like for example, if I punch you in
Mm-hmm. Mm-hmm.
your hand would be backing up.
Mm-hmm.
Why? Because my punch has a force.
Mm-hmm.
Apple has a force. Which is called mass. It has tons of atoms, and the atoms have weight, right? So due to the closing, or due to the atom is super close to each other, it creates
Mm-hmm.
something which is called mass, and the
Mm-hmm.
mass attract the object down, which
Why?
is caused a gravity.
How? 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 There's no
It's my
string.
perspective. It doesn't have to be true. It can be
Hmm?
false, I guess.
I mean, there's no string from from the earth to the apple. There's no string. So how does the earth pull the apple towards it without a
As I
string?
said,
Hmm.
due to the gravitational attraction,
Yeah, but there's
something
nothing.
which is being attracted by its mass.
How? How? There's no string. How? How does it?
Oh, wait. You want the equation? Do you want the equation? I have the
No,
equation.
no, I don't want the
Oh,
equation. I
yeah,
want the
sure.
explanation. I
I
can
just explain
understand.
it
No, you
due to
didn't.
mass.
No, no. That does that.
Why?
That's called begging the question. That is an
How is that
example
begging the question?
because
Begging the
you.
question is basically repeating your hypothesis as your claim or as an thesis. I didn't
No,
repeat them. I didn't repeat
no,
my hypothesis
no,
being as a thesis,
no,
but I
no,
rather
no,
give you an execute.
no,
You
no,
say why Apple
no,
fall. I say I think it's fall due to its mass. It's
no,
having mass. For example, for instance,
no,
if
no, no,
X, if
no,
Apple isn't
no,
having mass,
no, no, no.
no, no, no.
When I say no and you don't stop, what's the point of continuing the conversation? I said no, stop, and
Uh,
ask me what do you mean
sure. My
no?
my perspective, I think I'm true. From your perspective, you think I'm wrong.
When I
That's
say
why.
no, what's the point of having a conversation if when I say no you don't stop?
You're not being polite. You can't cut me off. That is not from politics or ethical conversations.
what's the point? Answer the question. What's the point of having a
Okay,
conversation if when I say no you don't stop? What's the point? Just answer the question. What's the point of having a
great,
conversation? It sounds like there's no
great,
point.
great. I would answer you. I would answer you. So
Hmm.
first, I don't think there is a point exactly, but I don't. I do think it doesn't have any point cause you ruin it. Like for example, if I killed someone, there's no point of him being alive because he's already dead. But then
I
it's
don't
my burden
understand.
because I killed him.
I don't understand.
Yeah, it's the same metric.
What's the point of okay? Why are we having a conversation? What's the point?
Anyways, yeah. Anyways, let's focus on your in your example
No. Answer the question. What's the point of a conversation? Why are we having a conversation? Why are you
to
talking
seek
to
the
me?
truth,
Excuse
to
me?
seek the truth,
Very good. Very
seeking
good.
the truth.
Very good. So if I tell you no, that means I found an error. I want to help you. So if you
And
are
you might be wrong.
maybe,
You might be mistaken. You might be
maybe,
false
yes,
comprehending.
maybe. But if
So
you're
maybe after I finish my sentence, you can find some information which prove to you that you're wrong or that you're
maybe,
mistaken. There's a
maybe,
reason.
maybe. But I'm already telling you that I feel that I found an error in what you're saying.
Sure, what's your error?
No. So no, no, we're not talking about that. We're talking about the theory of a conversation. Why are we having a conversation? Why should a person? Why do we want to? Do we really want to? Should we talk to each other? Is there a point to to
Yeah.
to have a relationship with other people? So if during a conversation you say something and I say no, 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 and you keep ignoring me, but if you're seeking the truth, let's say I would say something and you would say no. As I was saying it, I would immediately stop because maybe I made a mistake. I'm very curious why you think I made a mistake. So I would stop right away because I'm curious. I'm here because
Um.
I'm here because I seek the truth.
Sure.
And I
So.
appreciate anytime you have something to say, I appreciate it. I appreciate that you're here talking to me. You always run away. But whenever you do stay a little bit, I appreciate it. So
Thank you.
I think when I say no as you speak, I think it's very important that I think it would make sense that you as a truth seeker would stop and you'd be curious why I feel that you made a mistake. Maybe I'm wrong. We can have a discussion, a quick discussion. What's the point of you finishing your thought if I already found an error in the beginning of your thought? So why finish it? I already found an error. You're here.
Yeah.
You're here. We are both here so that we can stress test each other's ideas and clean up the ideas so that we can find the truth.
Okay.
Yeah. So I don't remember why I said no.
Oh. Sure.
That's
I was.
yeah.
I can remind you, I guess.
Go ahead.
You was asking me why Apple attend to fall, and I told you they attend to fall because they have mass,
Hmm.
and therefore they
Hmm.
are falling due to the attraction caused by their mass.
Okay, but
And you said no.
I don't think I would say no to that. That
I swear.
maybe, but everyone says that. What you just said, that's what everyone says. But
So if just
hmm.
wait, let me ask
Hmm.
you: do you
Hmm.
disagree with my definition or my
It's not. It's not.
reason?
Yeah, it doesn't make any sense because I can
Sure.
understand. Look, when I try to understand this universe, I try to understand this universe mechanically. I cannot understand a universe in which the Earth is grabbing the moon from a distance. And,
Yeah.
right? There's nothing between the Earth and the moon. There seems to be a vacuum between the Earth and the moon. So how is the Earth pulling? How is the Earth tugging on the moon? How is the sun tugging on the Earth? How is the galaxy tugging on the
Wait,
sun?
wait. Can I answer you?
Yes.
Okay, sure. You have told me before in your live stream when you were teaching me about dark matter and dark energy. You said dark matter is the reason why we are rotating around the galaxy. So I would take it as a reason too.
Well, the first question is why does the apple fall from the tree and accelerate towards the earth when there is no string attached? There's no string with which the earth is tugging on the apple. Why does the apple accelerate towards the ground? How does it do that? Well, how does that work? I never understood it until a month ago. It always bothered me.
So how did you discover it?
Well, I discovered it by solving Newton's equations.
Oh, appeal to authority, you mean?
Well, Newton's equations are based on Kepler's equations.
Oh, yeah. Wait.
You should
Yeah.
say,
What do you mean by an equation? What's your equation?
no,
Is it F equal?
you should, you should say Kepler appealed to authority. You should say that again. I said Kepler. I said Newton just used Kepler. You should say appeal to authority.
Why is it named as a Newton when Newton didn't do anything?
Right. I said Newton, you said appeal to authority. So I said Newton used Kepler. So you should say appeal to authority again.
Yeah.
Go ahead.
Huh?
Go ahead. Say appeal to authority.
Yeah.
What do you mean, yeah?
I
Again.
have said that.
No, you did not. Newton
I didn't.
used.
I just ignore it.
No,
I said, anyways, yeah, I
no.
believe you, I guess.
No. No, you shouldn't submit to an appeal to authority. Newton believed Kepler. You should say appeal to authority and throw the whole thing to the garbage.
But then you would be lying, and I didn't like.
Then
I don't love
fine. Then
hearing
if I'm
you.
lying, then we got rid of a lie. We are here seeking the truth. So
Yeah,
again, Newton used Kepler's equation. Say
appeal to
it.
authority.
Good.
You're appealing to authority.
Well, it's Newton. Newton appealed to Kepler's authority. Well, Kepler used Tycho Brahe's data.
Wow. Yeah.
What? Yeah.
Did
What?
you say
Yeah.
Tablo Krahi? Who's Tablo Krahi?
Tycho. Tycho.
What's
Tycho
wrong?
Brahe. Tycho Brahe. His name was Tycho Brahe.
What?
Tycho Brahe.
Tico.
Tycho Brahe.
What's wrong with your name?
That was
What
his
is this Tico
name. His name
Brahi?
was Tycho Brahe. There's nothing I can do about that. That was his name.
Yeah, he was an Indian, I can tell. He was an Asian.
No, no, no. This is in those days. I don't think India. I don't think. I don't think anyone knew India existed. This is
Holy
like
shit.
what?
He were born on 1546.
Show me.
Sure. Here.
That's how you spell his name. So he was
Wait.
born. Hmm.
Yeah. Well, I think you wrote it wrongly. It's not Teiko.
Hmm.
It's Teisho. Teisho.
Well, I don't know how you actually pronounce his name. I hear his name being pronounced by others. So
Yeah, sure.
let me see.
Anyway.
Yeah, he's Danish. I don't know how you'd pronounce Tycho Brahe. I'm assuming it's something like Tycho Brahe, but I don't know. Anyway, he had a fake nose, as you can tell.
Mm-hmm.
Yeah, so are you going to say appeal to authority?
Yeah. Appeal
So,
to authority.
wait. So, Kepler used Tycho Brahe's data.
Then Tycho Brahe is appealing to authority.
Whose
It's like
authority?
an hierarchy or some kind of paradox.
But he collected data.
Appeal to authority. It's with his name. You're trusting his information because it's from Tycho Brahe. But it's not how science works. Science works through empirical evidence, and we don't have any empirical information about his some kind of scientific evidence. We just
Look,
trust him because of his name, which would be appeal
yes,
to authority. And
yes,
I don't love appealing to authority.
yes. So, it's a good you're bringing up a very good point. So I'll tell you the story that is told, the mythology. The story is that Tycho Brahe used to spend all his nights on his rooftop, lying on his back, looking at the planets and writing down their positions. And he had notebooks upon notebooks of the planets and their positions every night throughout his entire life. So, would you say that Kepler appealed to Tycho Brahe's authority when he read his data, when he looked up the data, when he looked up?
Yeah, sure. Yeah, I have an argument which proved my critique, right?
Wait,
Which
would you?
prove that
Wait,
there is a critique within your argument. What I
no,
said.
wait. I don't understand what you just said. I asked you a question. Would you
Mm-hmm.
say so? Kepler used Tycho Brahe's notebooks after he died. So after Tycho died, so Kepler was his helper throughout his life.
Objection.
Go ahead.
Objection.
Go ahead.
All right. So I believe Tycho Brahe was some kind of flyer. Like, imagine I am saying there is some guy who's named Spaghetti Monster and he ascended and become a god, basically. So first, Tycho Brahe was living in 15, right, in 1500,
Okay.
and telescopes was invented in 1600.
Okay.
So Tycho Brahe was seeing the planet and the essential body, the celestial body, I mean, by his naked eyes.
Yes.
So it was super inaccurate. So for me to trust some invalid information and make up some theories about it would be a garbage. So basically, I don't have to trust him or give him any validity because I knew that he was reading his information by his naked eyes. So, what's your
Wait.
refutation?
Wait. So you're bringing up two objections. One is that he used his naked eye, and the other was that he's making up the data.
No,
No.
actually, no. I said
No. Hmm.
first telescopes was invented a decade after him,
Okay.
after he dies, right? Telescopes were invented a decade. Oh, your mic is
I
sounding
just
like.
tested the audio. Just I test the audio
Oh, my
once in a
bad.
while. Hmm.
Sure. So my premise would be telescopes were invented a decade after he dies, and claim,
Hmm.
therefore, or thus, his information were given by his naked eyes. Therefore, it wasn't accurate. So his information, his coordinates weren't accurate because it was made by a naked eyes. And we know naked eyes doesn't see anything above moon, some kind of stars. Therefore, his coordinates would be inaccurate. Therefore, his claims, or let's say his scientific evidence, would be garbage. It would be invalid.
I don't see why you say that. I mean, we can see the planets. We can see Venus. We can see Mars. We can
With with a telescope.
no, no. You can see a dot. You can see like a dot in the sky without.
No, wait. Do you have any proof? I'm not being hypocritical. I'm just asking you. Do you have any proof, like for your
I
claim?
think I don't remember if I ever saw a planet by myself. I don't
It
remember.
happens every. Yeah, yeah, I know it's an event. It's like an cosmic event which
No,
happen every 400 years.
no, 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 no. The
Oh, so.
ancients, no, the planets, the ancients named the planets. The word planet means nomads because the planets stand out from the rest of the stars. because the planets move nilly willy. The planets were always difficult to predict where they're going to go. The the whole star system, it rotates about the Earth perfectly, but the planets, they don't. They move nilly willy. They move unpredictably, like nomads, which is the word planets. Planets, I think, just means homeless, means nomads, like unpredictable, like people that roam, like roaming the sky. But the ancient
But
named the planets, the planet like Venus, that's the goddess of war or something, and Mars, the god of death or something, and Jupiter. These are names that the ancient ones
um,
gave to the planets. So the ancients knew the planets. At least I think three of them. I would say Venus, Mars, and Jupiter were known. Maybe Saturn also.
yeah,
And
it was Venus, Mars, Jupiter, Saturn.
okay. So even Mars is enough because Mars.
But
Go
I
ahead.
have a question.
Yes.
Sure. So what is those planets being seen by our naked eyes does entail? You can observe it from your eyes, but you can't say a coordinates. Like for example, you said yourself, you stated you can see planets as a small dot in the sky. So if you see a small dot, it would appear like a first dimensional from your perspective. It's a dot. Dot is a 1D, right? So for you, you can't do any coordinates on a 1D. It must be at least 3D for you to have a coordinates.
No.
So,
No. 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 Look,
oh,
the ancient ones, they had a cosmological theory. They used to believe that Earth was surrounded by a glass sphere. I think the word sphere even comes from,
glass,
yeah, a glass.
like real glass,
Yes,
like
real,
window
yes,
glass,
yes, yes. That was their cosmological theory. So they used to believe
super dumb.
what?
I say they are super dumb.
Well, they were pretty much accurate. What do you mean? They didn't know why the moon is not falling to Earth. So they said, "Oh, it must be a glass sphere that is holding up the moon." You don't have a better theory.
Continue.
So, okay. Right, so we think, oh, they're so dumb. No, they actually believed in science. That is the scientific assumption that the moon cannot just be there. The moon should fall straight to Earth, just like the apple. Ah, and we lost Mr. Andrew. Let's
Yo,
go.
what is it?
Yeah, did you see him? He disappeared. He just poof disappeared like he always does. Like he promised that he will not.
Andrew. Well, that's normal.
Yeah. And he's not gonna come back. And next time he's gonna give some cockamamie story why he had to disconnect.
It's
Anyway.
okay.
Yeah, yeah. He's okay. He's a good boy. Okay, here I'll give you the link so you can join me in the actual thing in my StreamYard so we can watch videos. Click the G9 link, please. Okay, I heard you. Yeah, I heard. There you go. Welcome. Welcome.
Okay, so what are we doing?
I don't know yet. First, let me see. Um, so I found this girl.
Well, she's cute, at least.
And she always shows her boobies, but she
Yeah,
seems
she
to
has
really
nice face.
yeah, but she seems to really know physics.
Okay, that's good.
It's like I don't know how old she is. Um, she's interesting, but always with her boobies. I think always, like even if she doesn't show them, she's cute. She makes sure that she looks cute. She always looks cute. I think she's I'm trying to figure out what is she. She's Asian. She's Filipino. Hey, wait,
Yeah, some kind of mix of Caucasian and Asian. Yeah, it's
wait. You're
probably like
speaking.
Filipino.
1 second. You're speaking simultaneously. Let me
Oh,
share this. Yeah, I'm sorry. Hey, Amber, where'd you go?
I went to take my medicine, so
Oh,
I'm a little
okay.
better now.
Okay.
you
So
can join it.
actually, so Amber, I'm actually on the line with Sinas, and we're gonna continue doing our research. Um, okay.
Okay, I'm gonna get some like quantum physics background
Nah, I
before the
mean
next time
you
we talk.
you can try. I mean that's what I'm trying to do. I'm just trying to figure out quantum mechanics, and it's giving me a run for my money. So you can try. I mean, you're welcome. I'll help you as much
And
as I.
yeah, I'm gonna get into it because like I used to have more of an understanding, but that was when I was working with somebody else and we talked about it all the time. It's like a language, you know what I mean? And then like you lose it when you're not using it.
Yeah, I understand. Anyway, let me get back to you when Sinus goes or whatever. Next time I have time, I'd like to continue talking to you.
Okay.
Unless you want to join us, but we're like me and Cena's like he's really advanced. He's even more advanced than me. So we're gonna be
No,
flying
but it's
through.
fine. It's perfectly fine.
It's up to you, Amber, if you want to
I'm just
join us.
gonna check in with Sophia in philosophy and then
Okay,
in like the bathtub.
okay. Then I'll see you around.
Yeah, see you around.
All right, thank you. Bye.
Jinx.
Jinx. All right. So anyway, I think she's Filipino, but
Yeah, probably.
and I don't know if she's. I think she's post high school.
Oh, she's an adult. I
She's
think
an
it's like
adult. Oh,
yeah.
okay. Really cute. Really cute and smart. Obviously, really smart. Look, she has a video. What is sound? So she's really, and she
Yeah.
defines. She says, "I'm Cheyenne." And I'll be your new physics tutor, Smiley. So, oh, Shy Physics is because her name is Cheyenne.
Or so
Anyway,
she says.
what?
Or so she says. Just so
That she's
she can
shy?
justify the name. Yeah, just
Yeah.
maybe. Who knows? All right. So what? So you're having trouble with that experiment?
I mean,
I mean, there's nothing to that experiment. That's that's the thing.
which experiment?
The one you were seeing in the previous live streams.
Okay, so let me go to
You were
history.
like all
Let's,
confused about.
yeah, let me see the history. Oh. So was this? She's a PhD. Her name is Angela Collier.
He's trying to see the
She's
cute girls. I see.
she
Playing
is
for the
a
cute
little
girls.
bit cute, but she's like an extreme leftist when it comes to science. She really
What does
worships.
that mean?
So she really
Oh, the
for her
climate stuff. Yeah.
it's not just I don't think she ever talked about the climate, but for her physics is a religion. So you can see what she says here. Why you can't explain QCD. I mean,
Yeah, if you can't
that's.
explain, you don't understand it. And
I mean,
that's the only answer. People,
if we go to her channel, then you'll see that she's basically against understanding physics.
oh,
Um,
that's great.
she's against. So why
That's
you can't explain QCD? What else?
a long-lived scientific debate.
Yeah, but I'll show you where it's clear that she's anti. She hates understanding physics. She wants to not understand physics. Just like, by the way, just like Zabine says in the
Yeah,
video. Let me find. Um, Let me find it.
video plots should not exist. Are violent.
Here, look at this. Can we space elevator? Should we space elevator? And she keeps saying we
What's
should
elevator?
not. What?
What's space elevator?
Oh, you don't know what a space elevator is? Wow. We will go. Okay, so we need to discuss that. But okay, we'll come back to that.
Is that
Uh,
like an actual elevator to space?
I'll show you.
So
It's
the
important.
aliens will not be silicon. Like, how do you know that?
Here, she has a video. AI does not exist, but it will ruin everything anyway. So it does not exist. This is the Heisenberg AI. AI does not exist,
No,
but it
but
will ruin.
I know what she's going for. That, yes. I mean, it's a
Okay.
catchy title. I know what she's going
No,
for.
but AI does not exist,
Yeah,
but it will ruin
it,
everything anyway.
it's a dumb thing to say that AI does not exist. Of course, AI
No, no,
exists,
no. But
and
she
of course, it
hates.
won't ruin everything.
No, no,
That's
no,
crazy.
no. She hates AI. She just hates
Why
AI.
does she hate AI?
She hates. Look, she's a hater, and we can. She hates understanding. She hates science. Um, Let me find
Why do
you
you think
some.
that AI will ruin everything? Why would AI ruin everything?
Well,
I don't. I never understand these things.
because she hates it. Because
Like
she
the only thing
hates
that
it.
can ruin things is like us using our technology to ruin the world. Like that's the only thing. It's not going to be our technology. It's going to be us using the technology in stupid ways.
Hold on. Look. Humanoid robots belong in the trash. So she's against humanoid robots. Um,
Okay, fine, whatever.
Harvard and aliens and crackpots. A
Oh,
disambiguation
so she
of.
hates Avi Loeb, of
She
course.
hates Avi Loeb. She hates him so much. He is the devil. And she has another video, physics crackpots, a
I
theory.
mean,
A theory.
of course, she's the true crackpot.
I don't
I
want to
think
say
we
that.
already know that.
I don't want to say that. And then she's against. Look at this. This is one of her first videos. That's when I got to know her. She was against naming the James Webb telescope after James Webb because he was an administrator and not a researcher. How dare we name a telescope after a NASA administrator instead of a researcher?
Whatever. I don't even
And then, um,
like. Who cares
anyway,
about that?
anyway,
That's so
so
irrelevant.
yeah, so that's her.
Okay, fine. I don't know why
Space.
you went through like a mini biography of her.
No, I follow her. I like her. She is she's a good physicist. She is one of the best teachers that I have. Uh Today I was listening to Why You Can't Explain QCD. All she said was that it's super mathy and that the only way to really do QCD is using computer simulations. And using computer simulations, that's not math. And because it's not math, it's not physics and it's not
Okay,
science.
that makes no sense. So
I know.
next.
But
That's a next.
yeah, yeah. Anyway, so what is a space elevator? That's actually, I'm surprised you don't know what a space elevator is. Let me show you a space elevator.
WBTG, what's that?
Actually, there's a space elevator in what's the Isaac Asimov trilogy? Empire? Space
I have no
Ele.
idea. I pretty much don't read fiction, so
Yeah, me neither. Um,
the only fiction I watch is crazy movies and action movies, stuff like that.
hmm. What is a good video? This is probably a good video for a space
You
elevator.
know, I'm all about space exploration, and I talked a lot about the challenges that we as a species face in doing it, whether we're sending people to Mars or just getting clean laundry to the International Space Station. So a lot of you have asked, why not get together as humanity and build a space elevator? That's an anchored cable system that reaches thousands of miles into space. Popular idea because on paper, the benefits are obvious. Launching a spacecraft currently costs about $22,000 per kilogram. A space elevator could potentially lower that number to less than $1,000 per kilogram. And just about every space elevator proposal follows the same basic blueprint. You have a base station that serves as your anchor point, a cable, a climbing mechanism, and a counterweight at the end of the cable. The inertia of the counterweight caused by the rotation of the Earth, not centrifugal force, would keep the cable taut. And once the climbing mechanism got above geostationary orbit, it would be pulled toward the counterweight. And look, I love the idea, but I'm just going to say it, we're going to be sending humans to Mars long before we have a space elevator. First, in order to remain stationary relative to the rotating Earth, the end of the elevator needs to reach at least 35,000 kilometers out into space. Ideally, it'd be more like 100,000 kilometers, which is like a quarter of the distance to the moon. Second, the counterweight needs to be really heavy in order to remain stable. Some have suggested harnessing an asteroid to act as the counterweight, and I honestly can't think of a better idea, given that the rocket power necessary to bring a man-made counterweight that far out into space does not exist. Third, and most importantly, we're going to need a cable that's insanely strong, light, and flexible, which pretty much means we're going to need carbon nanotubes. Everyone loves nanotubes, which have the potential to be 100 times stronger than steel and as flexible as plastic. They're made of molecular strands of carbon molecules arranged into hexagons, and they consist of more empty space than mass. Scientists have already constructed nanotube strands with a length to diameter ratio of 132 million to 1, which means that they're very long relative to their girth. But really long is also relative. The longest fiber yet manufactured is about 30 centimeters. So yeah, we've got a ways to go before we can build a
But this is 12 years ago.
Oh, I
35,000.
mean, okay, it's what I was thinking, but I just thought it was kind of unlikely that. Like, okay,
Look,
this is like a terrible idea. So
why
next,
is it a terrible idea?
it's impossible to implement this.
Why?
I mean, you kind of went through it.
What?
You kind of went through it.
We
Like,
kind would it
you went
he
through it.
what's the problem?
What's the problem? Everything.
Like what?
Everything about that, the length of the cable, the resistance of the cable, the counterweight, the the sheer amount of like building this, like who's gonna build, like who's gonna build this shit, like they have to climb up and they have to like be wearing oxygen masks all the time when they climb up. They're going to like need a ton of radiation protection, and you know, who knows. It's gonna be off the way to the moon, so it's gonna like go through the Van Allen radiation belt. That is insane. Like there would be like, you know, you'd have to isolate things so much in order to not have like constant uh, electrical shocks. Like you might as well try to build something that actually harnesses energy from the atmosphere that's really tall. You don't need to build something this tall and this complicated to do that, and it would have a lot more impact on humanity if you did that.
Hold on 1 second. Hey, Judas, I haven't seen you in a long time.
Hello.
Hi, what's up?
I don't know.
Where have you been?
Does it matter?
I'm curious where you've been. I mean, does it matter? Yeah, sure. I mean, I hope you've been well.
Yeah, let's talk about something interesting.
Okay, like what? What do you want to talk about?
No, I want you to decide.
I'm actually on the line with Sinus. We're doing our research. We're researching quantum mechanics.
Who is Sheamus?
He's a friend that we're doing research in physics together. Sinus, what's your schedule, by the way? Because I know it's late for you.
Yeah, it's late, maybe like half an hour or.
But you guys are neighbors. Sinus is very close to England. I think
Yeah, more or less neighbors.
you're the same time zone, I think.
Yeah, same time zone.
He's not in the chat.
He's not in the chat. He's actually in the StreamYard because we're watching YouTube together, so it's impossible to do it from here. You have the link. If you want to join us in the StreamYard, you have the link that ends with the G9.
How do I?
You click the link with the G9 at the end in the side chat.
Okay, I'm doing it.
Good. So you'll join us. Still waiting. Are you able to join us? Okay. I'm waiting for you. Okay, you're muting here, so I guess you're gonna show up in the StreamYards. There you are. Okay. All right, you're with us. Anyway, so we were discussing a space elevator. So Sina says a space elevator is no
Also,
good.
by the way. And
What?
he's already here.
What?
He's already here. I can see him.
Yeah, he joined us. You
Oh,
cannot see him?
Also,
Well,
yeah, I know.
he's
I don't
so
know. I was expecting to see him like in a panel or something.
he's in a panel, but
Okay.
your mic is. It says that your mic is not connected, Judas. I'm trying to unmute you. Oh, now it's good. Can you hear me?
Yeah, I can hear you.
That's good. So we were discussing a space elevator, and Sina says a space elevator is not a good idea. Do you know what a space elevator is, Judas?
Nope.
Okay, let's. So do you see the diagram?
Yeah.
Can build a 35,000 kilometer long space
So
elevator
let
cable.
me-
Despite all these, half the distance to the moon.
Here.
Second, the moon.
This is
Second,
the
counterweight
explanation.
needs to be really heavy in order to
You know
remain
what? Forget
stable.
about it. Anyway, so this is the idea of a space elevator. Where's the diagram? Let me get to the diagram.
Yeah, it's previous.
Previous?
Before.
Okay, maybe
More or
here.
less. Or you can just click outside of the video and it's probably on the thumbnail.
Means we're
Okay,
going
yeah,
to need carbon
no.
nanotubes. Everyone loves
Like
nanotubes. 100,000 kilometers, which is like a quarter of the distance.
Anyway,
Not on the thumbnail.
wait, Sinus, your audio is horrendous.
Probably. Is it better now?
We'll see. Anyway, there was a scene in Foundation with Space Elevator. Let me see, Space Elevator in Foundation. Judas, are you watching?
Yeah, I'm watching. I'm seeing some guy's face.
No, but Judas, are you watching?
Yeah.
Okay.
Expected return to home planet.
3 days.
Please respect and enjoy the peace.
This car will commence its descent down the stall momentarily. You may feel a jolt. Please secure yourselves before commencing descent.
So they live in the top of the elevator.
Yeah, I guess they're going down to Earth.
Oh, he's like a terrorist.
Yeah, he's a terrorist. So that's a space.
I was actually thinking about something that terrorists say when you started doing that. Like, is he doing it?
Wait, Sinus, I can barely understand what you're saying. What?
Yeah, I was actually thinking about something that terrorists sometimes say.
That's
Like,
that's
is he doing it? Yeah,
that's
it.
so that is the problem with a space elevator, and that's the problem with
And there
any
are a few more.
Wait, I can't understand what you're
There
saying.
are a few more, but that's one problem. Yes, it would be very easy to destroy.
Yes, and that's the problem, I would say, with every mega project. They're all susceptible to destruction. But this is why this is. Wait, somebody's making noise with the mic.
Yeah, it was me.
Oh, it was you? But this is the problem with civilization. This is why all civilizations are doomed. It's because it's so easy to destroy. You're making noise. Maybe you
No,
should mute yours.
It's not me now.
So, Judas, are you making noise?
One tab and open in 2 tabs.
Mm. So, Judas, do you understand what a space elevator is?
In space.
Wait, I can't understand you. We just lost Judas. All right, let's continue. Anyway, so that's a space elevator.
Why do you want to
Okay.
discuss that, though?
No, I didn't. You just didn't know what it.
Oh, okay. Fine.
It was for
it's
you.
fine. I don't mind.
Okay. Anyway, let's get back to our video. Wait. What's up, Judas? Judas, are you transmitting? You're showing us your video. Are you sure you want to do that?
I don't know how to turn it off, and now I'm so scared.
You can press. There is a bar in, and you can press the stop cam button.
It's fine.
But I don't know. Are you on like phone or something?
Wait, my camera's off now.
Yes, your camera is off. You're fine. I would not show your camera either way. But you guys, one of you is echoing horribly.
Still.
I'll put my headphones.
Am I still echoing?
I mean, I don't know which one of you is. It's impossible to tell. Let me do this. No, this.
Is it still echoing?
Um, I think it's Judas. We'll know when it happens again. We'll know.
I
Mm.
cannot hear an echo.
Okay, it's not an echo. It's like a noise. It's like a weird background. It's some sort of feedback. I don't know.
Yeah, I know.
Anyway, so whoever is not speaking should mute themselves probably. Wow, that's like really noisy. I'm assuming it's you, Judas, because you joined us last and that's when it started. Anyway, so we were gonna go back um to Zabin's video that I was watching.
Okay, but
This is
what do you still don't understand about that? We can watch your stream, yes.
yeah.
Your previous stream, it works.
I mean,
Oh yeah, oh that video was so insanely bad.
well, her video.
Yeah,
You think it was bad?
of course.
Why?
And she makes no sense whatsoever.
I don't remember.
Okay, let's not watch it. Let's watch Sabine's video.
Okay, let me open this guy.
Headlines. Last year's Nobel Prize in Physics was awarded for showing that the universe is not locally real, or for spooky behavior and spooky action at a distance, or for
Yeah,
exploring.
move forward to the experiment.
Okay. But maybe we should watch it like no, like like this maybe, so we can see. So I see everyone. I think it's better.
What's that supposed to mean? Is the universe really
So you wanna?
about today? That plan for mechanics, locality me reappear at JFK, off into the where things
You want to skip to her explaining the experiment?
side of the
Yeah.
past.
I don't think this is the oh, it is the video.
This one.
That's lovely. I really
So what's your
appreciate
problem with
the
this
company.
experiment?
Let's look again at that semi-transparent plate because it can teach us something very important. We'll now try to build a simple hidden variables model that explains what happens.
I don't understand when she says hidden variables model. The idea of hidden variables is that there is a hidden variable that controls the outcome of a quantum experiment. By the way, I was thinking about this today. Quantum has nothing to do with tiny,
With timing?
with being small. Because you can see an electron in a cloud chamber.
No, you can't see the electron in the cloud chamber. Like it's an effect that basically it electrifies the gas and it attracts like parts of the gas or it repels other parts of the gas
Let me
depending on what
see.
the gas is.
Electron
You don't
in
actually see the electron. Like that's not all what you're seeing. Yeah, just do that one. Sounds good.
This one?
Hey everyone, today I'm going to be blasting a cloud chamber with electrons. And I'd like to thank Mel Science for sponsoring this video. I'll tell you a little bit more about them later on in the video. So as you know, there's ionizing radiation all around us. It's continually whizzing past the air. In order to detect these particles, we have to make a cloud chamber. Now this may sound a little bit difficult to do, but it's actually not. It's really easy. I just spread some dry ice out here, and then I put this plate of aluminum.
So, Judas, what we're going to do in this experiment, we're actually going to see electrons.
No, we're not.
I think we are. If it works, then we're actually going to see electrons. Let me skip to the end.
No,
'Cause
not
you-
not
you-
so. No, that before that. Okay, there.
This?
Yeah, the explanation.
This is the explanation. I don't care about I want to see the result. Where's the result?
Okay, let's start with the result is like at around 4 minutes something.
You saw it?
Yeah, a bit more.
There,
Yeah,
here,
but
there it is. There is an
no, Judas
electron.
is gone.
What? Judas is gone?
Yeah.
Oh.
Okay, let's continue.
Yeah.
If he comes back, he comes back.
Yeah.
And then in this shot, we get a gamma, an alpha, and then a beta that goes right across it.
See?
See what you can spot coming off of my uranium sample here. There should be a ton of gamma and beta and a little bit of alpha.
So gamma is light, is high frequency photons. Beta.
I don't
Beta
know.
is.
I wanted the explanation first.
You want to
No,
see
I
the
mean,
explanation?
beta part. I don't think this is like radiation necessarily.
What do you mean?
It is. It has to be like kind of like radiation, but there are. It's probably like beta decay or alpha decay or something like that. Yeah.
Okay. Well, let's discuss the term.
That's radiation, obviously, but still.
Okay, so gamma is high frequency photons. Alpha, I don't know. I think maybe alpha is neutrons and beta is protons. No, beta I think is electrons. So alpha.
Okay, just see the explanation. You will explain
Okay,
that.
let's. You want to see the explanation? Okay.
Yeah, you don't need to
Actually
go
not.
from
It's
there, but okay, fine. Let's just see.
really easy. I just spread some dry ice out here. And then I put this plate of aluminum on top. And this is black aluminum, so I can see it a little bit better. All you really need to do this is some isopropyl alcohol. Now, the higher percentage you can get it, the better it'll work. So I'm using 99% isopropyl alcohol here. And I just pour the alcohol on the aluminum, spread it all around. I'm also going to spread some alcohol in the chamber itself to get a little bit more alcohol vapor. And I'm just going to put my vacuum chamber over top of it. I could use any clear glass chamber here, just any clear chamber that I can see through. And then just wait around 5 to 10 minutes for it to form a stable alcohol cloud in there. Okay, while we're waiting for the cloud to form in our chamber, let me tell you a little bit about our sponsor, Mel Science. If you like my channel and the physics to even their kids, I really recommend Mel Science kits because and click the link in my description, alcohol. Because the top is warmer than the bottom. Now let's get back to our experiment. What we're going to be doing here is creating a supersaturated vapor of isopropyl alcohol. Because the top is warmer than the bottom, as the vapor reaches the bottom, it's going to want to condense, but it needs a nucleation point to do that. Now some of it will spontaneously condense, and that's these little droplets that you can see in the air falling down. But then there's some of the isopropyl alcohol that is still in the vapor state that hasn't condensed yet, even though it's cold enough to do so. One way that we can get this supersaturated alcohol to condense is to create ions near it. When particles of radiation fly through the air, they can hit into the air molecules and knock electrons off of them. So once they knock electrons off, those air molecules are now positively charged. And so that can induce the isopropyl alcohol to want to gather around that charge.
Condensation.
Okay, supersaturated alcohol vapors. So I don't know what that is. Condensation trail. This is the condensation
Yeah, you
trail.
don't see the electrons. It's a condensation trail.
So the particle moves through. The red is the ionized gas atom. I don't know what that is. I guess it's the atom that has been stripped. The electron has been stripped off of it. This is an alpha particle, which is a helium. This is a helium nucleus.
Okay, interesting.
So there's just 2 protons and 2 neutrons. That's an alpha particle. Okay. There's no beta particle here, which it should be the same. A beta particle should be what?
Yeah, it should be the same.
It's just an electron, but everything else would be the same. What is this thing? So this is a
ionized.
No, he says this is a condensation.
Oh, that's like that's just how the condensation, the ionized gas atom is going to attract the other molecules.
Wait, the red. What is the red? It says
Ionized
ionized.
gas.
Oh, but why is it ionized? It's ionized because of the particle that went through it, stripped off.
Yeah, it stripped off some electron.
How?
So now it attracts negative charges. That's basically what this diagram is saying.
So each one is now collecting the vapor around it.
Yeah.
Because it's positively charged. This is polar alcohol molecule. alcohol mist droplet. This is a droplet. So a droplet is created, and the trail we see are these droplets.
Yeah.
Okay.
So it will
Okay,
actually make a
so the
small droplet
mystery
around
is
that positive
solved.
ion.
Wait,
There's
what?
nothing more to it. So the mystery is solved.
Well, I don't
We can go
understand.
back.
What?
Yeah, I mean we solved the issue. We can go back.
Okay.
So wherever that radiation particle flew through the air, you can actually see small droplets form as
I mean,
condensation.
you can
This is
go
the basic
back to
mechanism by which cloud
Sabine's,
chambers work.
What?
we can go back to Sabine's video.
No, I want to see the actual result. I want to see
Oh,
what he
okay.
sees.
Now, the interesting thing about these cloud chambers is that not only can you see the path that the radiation particles took through the chamber, but you can actually even tell what type of particle it is. For example, the most massive radiation particle is alpha radiation. This is a helium nucleus.
So alpha is helium, beta is electron, and gamma is just light.
Containing 2 protons and 2 neutrons but no electrons. These particles make a large wide paths in straight lines like this. They make straight lines because they have a larger mass and they're moving very fast, so they don't get knocked by the air molecules very much. Now the next type of radiation we can
But why are they moving?
Everything's
your beta
moving.
particles.
So beta are light, so their path is random, more random.
Beta particles are electrons that are moving very fast and they aren't contained in an atom. These beta particles are around 8,000 times less massive than alpha particles, so they can get knocked around by the air molecules, so they don't show up as straight lines as often. They make wiggly curved lines in the cloud chamber like this. Then we have gamma radiation. These are the high energy photons and they have no mass or no charge, so we can't see their path directly, but what we can see is the path of ions they create. So they can knock electrons off of atoms, or they can also spontaneously create an electron-positron pair that make their own paths in the chamber. So gamma particles look like small squiggly lines and wiggles. You can see a gamma particle here, and then a beta particle here, and then a straight alpha particle. And then in this shot, you can see a gamma particle here, and then a beta particle here, and then a straight alpha squiggly lines and wiggles.
Yeah,
You can see a
slow
gamma
down the video, or else you won't be seeing anything.
Okay. I'll go to half.
It could be.
Particle here. You can see a gamma.
I saw more than one.
Where is the gamma?
Particle here, and then a beta particle here,
Where? What?
Yeah, I don't see that one.
and then a straight alpha particle.
That I can see.
Yeah, that was okay. Again,
Oh, I see. It's just not pointing to the arrow is not.
You
well,
can see a gamma particle here.
I can
I
see the
see-
gamma particle.
I see
It's just very
something.
far from the thing.
And then a beta particle here.
Okay, so I guess there was something here that was beta-ish. I didn't
Yeah.
see. He said the first one was gamma, and okay, fine. I guess you can tell by the length. The gamma are very short, and sometimes they create electron-positron pairs. Okay. I'd be very surprised if we can actually see it.
And then a straight alpha particle.
Okay, where did it come from? Why did an alpha particle just show up out of nowhere?
It's just around in the environment, apparently.
Yeah.
Or he's having something that produces it. Like, get some like yellow stuff.
Yeah.
And then in this shot, we get a gamma,
Okay, so that's a gamma. Okay.
an alpha, and then a beta that goes
Okay, that's an alpha. Where's the beta?
right across it.
Wait.
Goes right. Yeah, a gamma, an alpha, and then a beta that goes right across it.
Oh, I
An
saw it.
alpha, and then a beta that
So that's the alpha,
goes right
and there's the beta. Goes across. Okay.
Oh, okay.
across it.
That was probably
See
gamma.
what you can spot coming off of my uranium sample
Oh, yeah,
here.
there's uranium there. That's why he has alpha particles.
Oh, okay.
Okay.
There should be a ton of
Wait. Why would uranium? Oh, uranium spits out alpha. No, uranium should spit out neutrons, not
Yeah.
alpha.
Alpha particles. It
But
does.
neutrons. Oh, you think alpha? Okay, let's see what he says.
gamma and beta and a little bit of alpha coming off of it. So we know that we can see beta particles, which are electrons in a cloud chamber.
Why do they keep calling them alpha, beta, and gamma instead? Now we know what they are. They should say like gamma is photon, beta is electrons, and alpha is helium nucleus. Why do they keep calling them alpha, beta, and gamma? I don't get it.
So what would happen if we actually blasted the cloud chamber with billions of electrons? So I'm going to create an extremely high voltage nail that's going to shoot a blast of electrons at the cloud chamber. Let's see what it looks like. I have a nail connected to one part of my Wimshurst machine, and then the bottom plate connected to the other side. Turn it on. Whoa. So what's happening here is the high voltage from the air is actually ripping air molecules apart and ionizing the air.
Yeah, it's got ionic range.
Here we go. 3, 2, 1. Whoa.
I don't understand what's going on. What's coming? What's going from where to where? All I see is I don't know what I'm
You have
seeing.
the terminals, and you can see the bright one is the source of the electrons.
The bright light is the source of the
The
electron.
bright one, the bright green one.
The bright green?
Yeah.
So this is not ionizing radiation. What it is ionizing the air very quickly and suddenly in the cloud chamber. And so it suddenly condenses all of the alcohol vapor in one big blast. This is my favorite one here. You can see an alpha particle go by right before this sudden blast. Whoa, that is so cool. Right before this sudden blast.
I don't know what's going
Before
on.
that.
Whoa. See an alpha particle go by
Oh,
right
you
before
can
this
see it,
sudden
I saw
blast.
I don't
I
know.
saw it.
Okay.
It's on the bottom right.
Okay.
Whoa.
I mean, we saw alpha particles before. It's
Yeah.
like no big deal now.
Oh, that is so cool. And because the alpha particle condensed the alcohol right before the big blast, that's where it didn't condense. So instead of single electrons at high speeds, we have a bunch of slow-moving electrons that are creating ions. And these ions make a sudden cloud in the cloud chamber. So this is really cool. Even though the electrons that I'm creating here aren't ionizing radiation per se, I'm able to ionize the air with this high voltage, and that ionized air then can condense in the cloud chamber. Hey everyone, thanks for watching another episode.
I don't get it. He doesn't explain this. A cloud chamber.
No, let's not watch more of this.
No?
No, like we get what it is. There's nothing special about it. Ether magnetic fields. What is that? Now I'm curious. What?
Alcohol or water,
that's
but
not Fossil
vapor.
University.
With vapor, and it's extremely cold in there.
Guys,
And
kind of crazy.
that's what causes it to condense in the air like a very, very dense fog. Now, anything that comes through that will really
Oh, he's watching somebody else's
He's
video.
watching the, oh yeah, is
interrupt the vapor, and you'll actually see it, and you're going to see it as we go forward here. Now, what's going to happen is that's just right at the top there. That is the little the electrode that will send down a pulse of electricity to the thing in the air. Show this. Oh, and it does that. Magnet is when in that.
If you look carefully, you can see the small trails of beta particles and the much thicker, whiter trails of alpha particles. If you look towards the top.
Let me just say, beta particles are the electrons.
Okay, I don't know.
Okay, let me just say.
Oh, this is the video that he was watching.
Here we have a cloud chamber in active operation. If you look carefully, you can see the small trails of beta particles and the much thicker, whiter trails of alpha particles.
Look, the point is that we can see electrons. So the first thing I would do is I would combine the double slit experiment with a cloud chamber.
By
Like
the
I
way,
would,
the stream is still talking to Amber, or talk to Amber. Yeah, I didn't change the title.
oh, okay. Okay, so this is talk to Amber. Space elevator. Cloud chamber. Okay, we'll see what else we'll talk about. So the first thing I would do if I had a cloud chamber, I don't know if it's possible to combine the double slit experiment or any one of these experiments with a cloud chamber. So if you want to see what's going on, okay, I would like to see the double slit, the electron double slit experiment combined with the cloud chamber, and I would put the cloud chamber just before the electron hits the detector.
Could be
You
an interesting
understand?
idea, but it would definitely change
Why?
the experiment.
Why should it? This is already after. It's after it went through
Oh,
the double. It's after the double slit. So instead of a detector, I want to put a cloud chamber. The cloud chamber should be the detector. I'm not influencing the experiment. This is the detection part. I'm allowed to detect the particle wave. And I'd be curious to see the electrons traveling in all different directions and creating the interference pattern. And then you would actually be able to see where it's coming from, what the electron trajectory is. Is it coming from the left slit, from the right slit, from between the slits, from somewhere else? Like, no, has no one done this? This is the first thing I would do. I mean, the double slit experiment, no one understands it. So why don't you do more experiments about it, around it?
Well, I mean, experiments cost money.
No, cloud
And
chamber? You see that everyone
no,
has a cloud
that's not the reason.
electron
No, no, people want to confirm theories. They don't want to dismiss theories. So
double slit experiment with cloud chamber. There we go again. Explained. No one does experiments. This guy 11 years ago, Mustafa Demirplak, he did it, yeah. This guy, he does us a favor. He shows a plate. He shows a photograph of the result, but he doesn't do the actual experiment. By the way, we can hear you tapping. I don't know.
oh, sorry.
What? Okay, it's okay. Cloud chamber. 10 years ago, Harvard Natural Science lecture demonstration. Okay. 7 years ago, double slit experiment explained again, as if we don't have enough explanations. Another explanation. Oh my god. More explanations. Explanations. What is it? 16 years ago. Okay. Uh, and this is really ridiculous. So they created a double slit experiment in time. So the electrons, probably not electrons, probably photons interfered with each other over time, not over space, which makes zero sense.
Like nature of light. As an experiment, just this past month, physicists at Imperial College London announced that they had been able to carry out the famous double slit experiment using slits in time rather than slits in space. Well, what on earth does that sentence even mean? This experiment, other than being cool to a optical physicist, someone who likes studying light, also confirmed that behaviors in time and space are correlated, and has actually resulted in an advance in our understanding that may help us one day make computers and bits out of beams of light rather than out of electrons and silicon. Computers made out of light, slits in time, sort of feels like someone's put a physics textbook in a blender. What is going on here? Let's take a dive into this kind of strange experiment. Okay, I want to start with a quick crash course on the regular double slit experiment. Then I will run through how this research team conducted their experiment in time rather than in space, which already sounds trippy and confusing. The first, now classic double slit experiment was originally proposed in 1801 by British scientist Thomas Young while he was exploring the wave-like nature of light. As a light was shone onto a card which had two slits cut into it, the waves of light propagated through the slits, and when they reached the screen at the far end, they produced an interference pattern of bright and dark bands. Where two peaks in the wavelength of light overlap, you get bright spots, constructive interference. If a peak of one wave overlaps with a trough of another wave, however, you get no wave at all, which is called deconstructive interference. This was actually one of the observations that confirms to us that light isn't as simple as just a particle, which would have otherwise produced.
So, by the way, a photon is a wave, is an electromagnetic wave. It's a wave in the electric and magnetic. It has both. I mean, it's an electromagnetic wave. Did you hear my latest realization? Is that every wave. Let me ask you a question. Have you ever seen an infinite wave?
An infinite wave, no.
So I'm assuming every wave you've ever seen is a finite wave.
Yeah.
So what's the difference between a photon and every other wave in the universe? Or an electron? I mean, why are we surprised? Why is Einstein's 1905 paper about the photoelectric effect, and why is Planck's idea of the photon? Why are they supposed to surprise us? A wave is always finite. So the only surprise is that there is a minimal size. It's not quantum. Every wave is quantized. There is no unquantized wave because waves are always finite. So all waves come in quanta. But the discovery of Planck is that there is a minimum size. That's the discovery. Every wave is a quantum wave, but not every wave is a minimal wave. So an electron is such a wave that cannot be split in two. A photon is such a wave that cannot be split into. It's a wave. It's a finite wave like every other wave. Like you go to the ocean, you go to the sea, you go to the beach, and you see waves. Those are finite waves, like all waves, but they can be split in two. An electron is a wave, and a photon is a wave that cannot be split in two. So the fact that they can go through double slits, that then becomes bizarre. That's weird. That thing which we're saying cannot be split in two, suddenly we're splitting it in two. So now I'm confused. We just said,
Maybe we can split it into.
but if you can split it in two, then what's an electron? So you should have half electrons and quarter electrons.
But can you do that with an electron? Split it into.
What?
But can you really do that with an electron? I know you can do that with light, but with a photon. But can you do that with an electron?
The double slit experiment?
Yeah. Does it work the same way as with a photon?
I mean, that's what the
I asked that question to ChatGPT, and ChatGPT said it doesn't work the same way. That you can't actually divide an electron. It's different.
Where is the double slit? This is an
Now we are looking at the detector plane on the monitor. Bright spots appear. Now we are looking at the detector plane on the monitor. Bright spots appear here and there. These spots indicate individual electrons. Electrons are sent out only occasionally. Therefore, the chance of finding one electron in the microscope is very small.
No, these are not individual electrons. This is already wrong.
What?
These are not individual electrons. That's this is like a photographic film or something like that, or some kind of solution, and it just it just reacts to the old ink when it's struck.
So you're saying every double slit experiment is wrong because
Not
it's always
every double slit experiment is wrong. Generally speaking, when you see on YouTube, they don't explain it properly.
no. What you were saying, it's
Let's keep watching. Let's keep watching.
Wait, but what you? I'm actually considering seriously what you're saying. It's possible. Okay. It's possible that every double slit experiment ever conducted is wrong because it was always more than one particle going through, and that's why there is an interference pattern. It's not because it's a single elementary particle wave going through, because if it would have been, it would have only been able to go through a single slit and not create an interference pattern.
Okay, but let's see if he actually creates from one electron.
But
what actually happens with one electron?
But he already said that these are electrons. And he didn't.
These are electrons, but that's when he shoots many of them. I want to see when he shoots only one of them.
But he doesn't shoot. He just says. He doesn't show you the apparatus.
Okay,
and he doesn't.
But
yes,
I'm not surprised. Okay, well, let's see to the end. Let's see to the end of the video.
Since electrons are detected one by one as particles, we have to conclude.
He says they're one by one as particles.
Okay, that's ridiculous. That's one by one.
He doesn't prove. He just asserts.
I mean, yeah, it makes sense that they are a particle. Like given what is showing, but this could also be a deflection of a very, of some kind of like reflected thing. But I mean, from what he shows, the experiment, it should be consistent with the experiment to interpret this as a particle. But let's continue.
The question is, when he says electrons, he says since electrons are detected one by one as particles. I mean, this is an assertion. You didn't prove it. We have to.
I mean, like he doesn't see the interference pattern. That's basically what. It just sees like
I mean,
dots on the screen.
No. He will show an interference pattern, but I'm saying it's not. Each dot is not a single electron. Each dot is.
This is like a noise detector of sorts.
I don't know. There's no explanation. I mean, We can look at. I don't know what is Hitachi Ltd. I mean, I guess this is the name of the camera or something. What year is this? This is 11 years ago. I've uploaded this video for educational purposes only. It has been retrieved from Hitachi's website. However, the video is deleted after Tonomura's death. Please let me know if any copyright is violated.
Okay, don't worry about that.
No. This is important. I mean, what are we looking at? I don't know what we're looking at.
That each electron must pass through at random on either side of the pi boson, thus creating a uniform distribution without any interference when accumulated.
Oh, so he's saying this is uniform distribution. Wait.
Okay,
Since electrons are detected one by one as particles, we have to conclude that each electron must have passed through at random on either side of the
Okay, one
biprism.
electron. There's nothing amazing about this. Like one electron.
Wait, thus creating a uniform distribution without any interference when accumulated. So, what is the setup? I don't understand.
At random on either side of the pi boson, thus creating a uniform distribution without any interference when accumulated. Under such condition, do electrons form a uniform distribution? But look, we begin to see some fringes in the perpendicular direction that looks like interference fringes. Since this experiment lasted for more than 30 minutes, I have sped the movie up. Interference fringes are now clearly visible.
I don't know. I don't know what the setup was.
Interference. Okay, so there is interference after all.
What did we?
So he just spent some time saying the opposite of what he said in the end. Okay, fine.
I don't know what we watched. I honestly don't know. We just
now
it's not a one electron, by the way. I don't know what it. No explanations, please.
Yeah.
Just no. That guy is not going to show.
Yeah. He's not going to show anything. Yeah, we know that what we can do.
Okay,
Obviously,
so after all, the electrons are actually working kind of as waves. Because they show an interference pattern, but there's nothing strange about that. Like if they have similar spin, that it should be the same.
Spin?
Yeah.
What do you mean spin?
I mean, it depends on how the electrons are being shot. Like if they're being shot with an electron gun and they go with the same spin and they get into phase with each other.
What?
It should work like that.
I cannot understand what you're saying, and I don't know what you're saying.
Okay, so imagine electrons are being shot in all the same way, so they should have similar spin.
Spin? Why are you talking about spin? Why are we talking? We're talking about the double slit. Double slit doesn't have spin.
It does technically. Like.
What do you mean? How?
Like there's always spin.
How is spin related to the double slit experiment?
Well, I mean, it's related to interference.
How?
Polarization is related to interference.
Okay, but there's no polarization with the double slit.
There is, of course. There has to be, like, you. Otherwise, you just get weird shit. You have to get like clean interference. Fringes usually need to, I mean, lasers. Usually, the experiment is done with lasers. So lasers are polarized, usually in one direction. So an electron gun should also be sort of like polarized as well.
Well, an electron, I don't think we can polarize an electron.
Well, it's just the spin, like that's the equivalent.
I don't know what spin is. I don't think we know what spin is. I'm confused by spin. They say I don't know why you bring up spin. No one ever brings up spin with the double slit experiment. So this is you're the first person to discuss spin with the double slit experiment.
Okay, maybe. But if you think about it, like if you think about this as electrons bumping, it would still work in the interference pattern.
I don't understand what. If I
If you
what?
think about this as electrons bumping into
What
each
do you
other,
mean?
oh, there's one experiment that they brought spin. Like you remember that experiment that I was telling you about the curl?
The
Like
curl?
yes, like the Abramov bomb experiment. Yeah, the one that had a solenoid in the middle, and then the electrons would change their spin and it would change their interference pattern.
Okay, but
Right?
we're talking about the double slit experiment right now.
Yeah, that is a form of a double slit experiment, but with the solenoid in the middle.
Okay, but that's not. Look, in the
Yes, but
double
you could
slit.
see in that experiment that the spin altered the interference pattern.
What? I can see what?
In that experiment, you could see that the spin was altering the interference pattern.
But I don't want to. We can talk about that experiment, but we're talking right now about the double slit experiment.
Yeah, but the
So,
spin alters the interference pattern.
wait, in the double slit experiment, you're
Look,
saying
the
this.
the first phase of that experiment is just the normal double slit experiment.
What do you mean, first phase of that experiment?
The
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 double
part the
slit?
doing that experiment without the solenoid is literally just a double slit experiment. And
Yes,
then
we're
we put the
talking.
solenoid in the middle.
Look, I was just looking up to see if anyone ever conducted the double slit experiment with a gas chamber, with a cloud chamber, not a
Okay.
gas chamber.
But you can see that spin does alter the interference pattern.
But I'm only talking about the double slit experiment. I don't care so much about the solenoid experiment because I never really understood the point. So I never. I'm not even thinking about spin right now. I'm still confused about just the double slit experiment. My
Okay, what are you confused about specifically?
I'm confused because we're saying that an electron is is the smallest wave slash particle such that it cannot be split in two. And as soon as we say that, the next thing we say is it goes through two slits
No, but
simultaneously.
we're not sure of that yet.
No, 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 no. There's no such thing as we're not sure of
No, we're
that.
not sure of that yet. Like we haven't verified in any experiment here that like I asked ChatGPT this question and ChatGPT says no, the electron cannot go through two slits at the same time. The photon can, but the electron cannot.
But
That's what ChatGPT says.
The broil said that there's no difference between an
The broil or
electron.
the broccoli?
What?
What's his name? Is that the broccoli?
The broil. You pronounce
That's
it the
his name. You
broil.
pronounce the okay,
You
fine.
don't
But
pronounce.
I
You
mean,
don't.
what he said and what someone else said is whatever. I don't really care.
So you're denying the broil's principle?
I don't know. I don't care about opinions.
But so you're saying the electron double slit experiment was never conducted?
No, I'm pretty sure it was conducted, but I wanted to see one with a single electron, but just to confirm whether what ChatGPT tells me is correct or
So
not.
let's ask. Let's ask. I'm tired of asking YouTube, so let's ask either Google or ChatGPT. I guess we
Yeah,
can
let's go
ask.
to Google first.
Okay. So how do we know? Okay, I think we need to ask ChatGPT. Where's ChatGPT? Do I have ChatGPT? There it is. It's going to ask me to log in. Hold on 1 second.
okay. I'm still seeing YouTube.
No, because I'm logging into
Oh, okay, fine,
ChatGPT. I don't want people to see me logging in, even though there's nothing special.
fine.
Okay, so in the electron,
The single electron double slit experiment.
well, that's the question. In the electron double,
No, single electron.
well, hold on, that's the question. In the electron double slit experiment, how do we know if a single electron went through? Okay. In the electron double slit experiment, we can detect if a single electron goes through the slits by using a sensitive detector on the other side of the slits. Here's how the process generally works. Single electron emission. Electrons are emitted one at a time towards the double slits. How do we know that? This ensures that at any given moment, only one electron is traveling towards the slits. But how do we know that it's a single electron? Detection screen. On the other side of the slits, there is a detection screen, such as a phosphorescent screen or a modern digital detector that registers the impact of electrons. When a single electron strikes the screen, it produces a detectable event, like a small flash of light or a signal in a sensor. How do we know that? Recording the impact. Each time an electron hits the screen, its position is recorded. Over time, as more electrons are sent through the slits, a pattern begins to emerge on the screen. Interference pattern. Even though electrons are sent through one by one, how do we know that? Single electron. To determine if a single electron went through, we don't directly observe its path with the slits. Instead, we infer its passage based on the eventual detection. Okay, that doesn't answer the question. Let's go to Google.
Okay, no, it answers the question perfectly. So a single electron is just is not going to produce an interference pattern.
What? I don't understand.
No, it answers our question. But a single electron can't produce an interference pattern.
What? How do you know that a single electron went through? Maybe two
Okay,
went
you
through.
see the thing on the detection screen.
What?
You see the dot on the detection screen.
How do you know that's a single electron? Maybe it's multiple electrons.
Yeah,
How do you know
maybe.
it's That's the question. If it's multiple electrons, then and they behave like waves, then they can interfere with each other. By the way, when you look at with the cloud chamber, it doesn't look like a wave. It looks like the streak of a particle. What I'd like to see is I'd like to see a combination of the cloud chamber with the double slit experiment. I doubt they'd be able to reproduce the interference pattern then.
Yeah, it would change a bit.
I mean, I'd like to see a cloud chamber, then the double slit, and then a cloud chamber again. Like as it goes through the double slits, I'm willing to forego the cloud chamber. Fine, let it go without the cloud chamber. As
But
it goes,
afterwards, it's impossible. Like afterwards, it has been detected, so it has hit the screen.
wait, what?
But afterwards, it has already hit the screen. So
But afterwards, it what?
afterwards, it can't be after it hit the screen. So it can only be like after it goes through the slits.
I don't
But
understand.
that would be interesting, so you could see the path after the.
I mean,
the
I want to
slit.
see. I want to see the path before it goes through the two slits.
Oh, okay.
As it goes through the two slits, I'm willing to not look.
Oh, I see.
And then right after it goes through the two slits, I want to track it again with the cloud chamber once again. So I should be able to see a single streak heading towards the double slits. Then it should become, then when I'm not looking, we're not detecting the electron, it should become a wave, go through both slits, interfere with itself,
No,
and then
electrons can't do that.
what?
Electrons can't interfere with themselves.
Okay, I mean that what you're saying is against what everybody is saying.
No, look at what ChatGPT is saying here.
What do you mean?
Okay, ask ChatGPT if an electron can interfere with itself.
I mean, here is the evidence. I
No,
mean,
ask ChatGPT that.
okay, I just want to make sure we both agree. Here is the evidence. It's the evidence is
No.
this
We are
is.
looking at the detector plane on the monitor.
I mean, this is the. So what? Okay,
I disagree.
explain. Fine, then explain this experiment.
Explain this experiment. Okay, you get an interference pattern in the end, but that doesn't tell me much.
Okay, explain the experiment. What is it? What is going on here? Explain.
So it's detecting like individual single photons, electrons, right? Like supposedly, like they're eating that part of the screen and in interacting with like the phosphorus or whatever is there. And at some point, the pattern begins to emerge. So it's quite probable that the electrons are waving until they reach the screen, like they're little wavelets, as you say. So but that doesn't mean that they're like interfering with themselves through the slits. That doesn't necessarily mean that. I mean, you don't need to interpret it like that.
I
They
mean,
can
just
just pass through one slit and be somewhat deflected.
but then you wouldn't get an interference pattern. You would get a
You would after shooting a lot of them, because there would always be zones that given the wavelength, or given the wavelength and given the wavelength, they would be black. They would not receive a lot of electrons. This is just a zone of higher probability and a zone of lower probability.
Wait. So explain again this experiment. What are we seeing?
Okay, we're seeing an interference pattern,
Yes, I
right?
agree. Mm-hmm.
So if so, we can imagine this as like an electron goes through one slit and gets somewhat deviated.
But then, how are you? No, because then how would you get an interference pattern?
How would I get an interference pattern? Okay,
Yeah.
let me think about it. So an electron could go like straight through one of the slits, right?
No. Again, you would not get an interference pattern.
This is an interference pattern after many electrons.
Yes.
So it
Yes.
just means that it's less likely for them to end in certain zones.
But there's no indication. There's no indication that it went through one of the slits. All the indications are that it went through both slits and interfered with itself. That's what it seems to indicate.
Let me think a little bit more about this.
There's
So,
an there's another problem. If we would shoot two electrons at once, because they're both negative, they would repel each other. They wouldn't want to be together.
okay, more or less, but that's not too important.
No, because I mean, anyway, we need a cloud chamber. I don't know. I don't understand. I mean, the quantum world should be really straightforward. As far as I'm concerned, it should be like special relativity. It should just be wave mechanics. It should be
But
waves.
you can think about this as like the electrons would bump into like they would, okay, so
No, no, no,
think
you
about
can't.
this, like you're sending them one by one. Okay, so you're sending them one by one. So they would have to be forced to go through one of the slits. If they were to be forced to go through one of the slits, then what
Then
would happen?
you would not see this. I mean,
Yeah,
you
I
you
probably
would
don't see that.
you would see two slits, not many slits. This is what we expect to see because of an interference of an interference.
Yeah, that's what you expect to see over an interference. But I'm thinking if you could get this in some other way. Like if you imagine that the electron is somewhat waving in a way, like it's causing some kind of
Look,
waving through the medium,
look, because I
then uh, then it would quote unquote interfere with itself, but it would still go through one of the slits, right? Like it would go through one of the slits, but then the waving in the medium, the wave produced in the medium, would then interfere with the path of the electron and create a pattern like this. Seems to me that something like that is what's happening. But ask ChatGPT, like, why do we see an interference pattern? Because this could be an interaction with the medium. Like, if the medium is waving, then the medium will basically carry the electron.
but the medium waving is the ether waving is the
Yeah.
electron. That is the electron.
Okay,
The
that's one
waving.
possible interpretation as well.
Otherwise, you don't have conservation. You lose. This universe doesn't have conservation. You don't conserve. You lose everything. Everything.
No, you don't lose conservation with neither one. But this is it's like
What
the
do you
question
mean?
here is what is really an electron? Like without knowing that, there are various possibilities for why this is happening. Like
Okay.
it's an interference pattern, yes, but it's caused by what? Is it caused by the medium or is it caused by the electron? Or is it the same thing? You know, is the electron just part of the medium? It's yeah, there's a few ambiguities here that are difficult to answer. Like try asking ChatGPT why does it produce an interference pattern?
Why? Why do you want me to keep asking ChatGPT? I mean, we need to
That's
think
what it
this
says.
through.
It's just throwing paint at the wall. So
I mean, I'd rather think about it than ask ChatGPT.
okay, you can also think about it.
Yeah,
Let
let's
me, but
think
let me
about
read
it.
what it says on the interference wave.
What?
Let me just read what he said about the interference pattern.
What do
Okay,
you mean?
down, go down. Yeah, okay, interference pattern.
So even though electrons are sent through one by one, the positions where they land on the detection
Okay,
screen
behaves as if
gradually
it interfaces itself. Okay, so
form
it
an
says the same as you.
characteristic of wave behavior. This pattern suggests that each electron behaves as if it interferes with itself, as if it went through both slits simultaneously in a probabilistic wave-like manner. I wouldn't
Okay,
say
that's like saying
this.
you don't get what's going on. But
No, no. Look, when he says in a probabilistic wave-like manner, that's nonsense. That does not make any sense. But everything else makes a little bit of sense. The question is, the only problem I'm having is we claim that an electron is an elementary particle. So it cannot be split in two. This universe.
yes, that's the problem. Clearly, either the electron isn't an elementary particle or the wave is not the electron. Like you have one or the other.
So what's going on?
So what's going on is a good question. We need more experiments to know.
What is this? Okay. I mean, I'd like.
You could imagine this as like the electron is some kind of vortex in the medium that when you accelerate it turns into a wave. That could
No.
be one.
My intuition is that everything must. My intuition is that everything must be a wave. You cannot have anything but waves. So when you see the electron as a particle moving through the cloud chamber, that's weird.
I mean, it's not really as a particle. What you see is a condensation trail. So
But it shouldn't be
different. And it's like it's like you can imagine it as an exchange of energy between various
The question is if we imagine it is a wave. I mean, I would like to use I think they have particle detectors where they detect electrons. Let's look for an electron. There's many more experiments where they looked at electrons. Even they looked at an electron in an electron microscope.
Really? Is that possible?
Yeah, they did imaging.
Okay, we can see that.
Dynamic imaging with electron microscopy. Scientists in Sweden film moving electron for the first time.
Fighting on a light.
Okay, let's see.
Scientists.
This is 16 years ago.
Used a device called a quantum.
Yeah,
Swedish
it looks
researchers
like
released
a
video
field.
ever taken
It
of an
looks like a standing wave. Okay, so you're probably right. It's a standing wave.
electron. Swedish researchers have released the first clear video ever taken of an electron riding on a light wave. Scientists used a device called a quantum stroboscope to freeze the electron's motion at different stages, just as you would freeze a hummingbird's wings in flight using a regular stroboscope. The resulting video has been slowed down and looped to show the motion clearly. For MSNBC.com, I'm Alan Boyle.
What's a stroboscope?
I don't know. Oh, strobe, it shines light off and on.
Sweden.
When you picture an atom, you might picture it like this. A positive nucleus. When you picture an atom, you might picture it like this. A positive nucleus with negatively charged electrons.
What?
Oh, I see what they did. Okay.
Electrons orbiting around the positive nucleus. After all, we always talk about electron orbitals, so it seems natural to picture them orbiting. This model of electrons orbiting a nucleus was proposed in 1909 by Ernest Rutherford, and it was called the Rutherford model. He said you can picture an atom kind of like a mini solar system, with a high-density nucleus at the center and the lighter electrons orbiting at high speeds around the outer edges. But there's a major problem with this view. If an electron's orbiting, then it has a constant centripetal acceleration. And when a charged particle accelerates, it gives off radiation, so it loses energy. So we can calculate
I don't think he's going to show anything.
how many
No, I
seconds are about
don't
0.5
think.
isn't true since you're making waves around the nucleus of an atom. If I vibrate this ring slowly, nothing happens. But as I increase the frequency, it suddenly starts to resonate. So we now have a standing wave in a circle. This looks so cool. But notice something
Okay,
here.
this
I can
is
increase the
cool.
energy by turning up the frequency of
This is very interesting. This is the Bohr model.
vibration. But suddenly the resonance goes away and it just looks like a normal ring again. But then suddenly if I keep increasing it, then I get another standing wave. This time with more nodes. And then another higher mode here. There's another one.
This is Bohr's model, and Schrodinger's equation basically agrees with this, just in more dimensions.
And still finally one higher one here. Notice that I don't get any standing waves in between these frequencies. So there are only certain energy inputs that are allowed in order for standing waves to occur. For a standing wave to form in a circle, an integral number of wavelengths must fit with...
Which makes sense. I mean, it's a wave. It's waving somehow.
in the circumference. This means that only some discrete wavelengths are allowed to form in a circle of a given radius. What's happening here is exactly what Niels Bohr proposed is happening in an atom. The electron can only increase in energy with discrete intervals, just like in our ring experiment here. The ring doesn't vibrate unless I give it some specific energy input. So the energies of this ring and the energies of electrons are quantized, meaning that they only come in discrete packets. So they found that it's necessary that electrons move to different vibrations through quantum leaps. There's no smooth transition from one vibration to the next. They jump to different...
They discovered that there is a smooth transition. It's okay. That was, yeah. It is a smooth. Of course, it's a smooth transition, but it is a transition.
Vibrations that we still call orbitals, even though nothing is orbiting. The resonant frequencies of an electron look like this. These are the possible orbitals of an electron orbiting around a proton. But that leads to another question.
But these are the orbitals. These are not the vibrations.
In this experiment, we have a ring vibrating.
I think. I mean, you can have vibrations within an orbital. I think no.
But in the case of an electron, what's actually vibrating? And before we continue, I'd like to thank the sponsor for this video, BetterHelp.
What's actually vibrating? That's the ether. Let me skip that.
The network. Then you can talk to your therapist however you feel comfortable. Therapist isn't the right fit, but with a therapist who is custom in the description. And thanks for BetterHelp.
We should contact BetterHelp. Maybe they can help us with the electron.
For sponsoring this video. Now let's get back to the experiment. So what's actually vibrating in the case of an electron? Well, the truth is there's...
I mean, we could use them just to, talk to them about we don't understand. Look, it's bothering me. I can't sleep because of this. So, please solve this. It's your job.
Nothing physical that's actually vibrating. Whenever we try to measure where an electron is, we never see it spread out in a wave like this ring here. We always see it as a little particle, never a wave like we described here. For example, in the first resonant frequency of an electron around a proton, it looks like this. This is also called the s orbital. But when we measure where an electron is in a real s orbital, we find that it's here, or here, or here, or here, or here, or here, or here. It always is in some random spot. But when we measure it a lot of times, we find that where the dots are spread out in space start to look like the original electron orbital looked like. So what we find is that the electron orbitals show us the resonant frequencies of an electron, and this helps us know where the electron is likely to be found when we measure it. So if we take the square of the wave function of the electron in a specific orbital, we find that it gives us the probability of finding an electron in that specific place. So a vibrating ring can become a great analog for understanding electron orbitals, but it's not perfect. Another difference is that the ring provides modes with an odd number of half wavelengths, but a Bohr model to the atom allows modes with an even number of wavelengths. And the reason for that is how the ring is actually attached to the vibration apparatus. And thanks for watching another episode of the Action Lab, and we'll see you next time.
Well, because the way it's attached is... really, we should take a ring it should be in free space and let it vibrate without holding on to it anywhere. And then we'll get a better understanding. Okay, whatever.
Skip.
All right, so hey everybody.
Skip.
At UCSB, and I'm going to show you some atoms. So this
Wait.
huge car-sized block, standing transmission joke. But either way, I'll learn something. So this is going to be like.
Why is he using a mask alone in the room?
Oh, I think it's a clean room, maybe. Or maybe it's Corona. Maybe it's from 2 years ago, I guess.
Imagine, shining a piece of light. Trying to shine a light. So they're both the same thing. It needs to be more resistant. From one of my previous videos, that's on this tiny flake of copper. But to see it, we're going to have to zoom in. You can see a bump on the side. That's my sample. Looking even closer, hopefully you can appreciate how this entire sample is a vanishingly thin flat where I'll be imaging, somewhere in the range of about 150 atoms thick. And this is what we'll be shooting electrons.
80 nanometers. That's 10 times smaller than the wavelength of red light.
Through to cast our shadows. Even though this copper crescent is vaguely...
Red light is about 650 nanometers, 0.65 micrometers.
100,000 times larger than the dimension we care about on the sample it's holding, it's still small enough that it's a pain to work with. So to help, we've got these fancy vacuum tweezers. Basically a tiny hose that sucks up the sample like a piece of cardboard stuck to a shop vac. This is more than a little finicky, and while trying to bend around to give the camera a good view, I actually dropped it the first time. Crud. Something like this could only happen when I tried to film it. Thankfully, the sample itself was all right. It's also worth appreciating that even this tiny sample stage is itself a miniature engineering marvel. It's designed to tilt the sample in two directions without translating it in X, Y, or Z by more than a couple microns. It's absurdly precise. This is actually some microscope footage from a time that the holder actually broke. I swear, I was not pushing on the clip any harder than I should have. But you can see that the hinge here that broke isn't a normal ball bearing or something like that. It's actually a ruby, like literally a polished gemstone that runs in a groove. So now that the sample is mounted inside of this chuck, if you'll follow me around the corner, in here.
That's why he's wearing a mask, so not to breathe on it.
Oh, I see.
We have the actual microscope. Like all electron microscopes, the stem here is basically just a big multi-compartment vacuum chamber, which means that this thing, when I load it into the chamber, needs to be able to stop all of the air from rushing in behind it. When I put this in, it's actually going to create a seal at this O-ring, and then I'm going to have to wait for a few minutes while it pumps out the airlock before I can push it all the way into the microscope. There we go. Now it's a pump start. And don't worry, if I made trying to look.
So as soon as it went in, the vacuum was created or something?
Look, that sample look awfully tedious. Just wait till I get to the part where I focus the microscope for an hour. Just like that. Air pressure pushes it right on in. I don't even have to do anything. A transmission electron microscope is basically casting shadows with a beam of electrons. You're shooting a high energy beam of electrons all the way through a material, and you're projecting whatever gets through out onto a screen and looking at that image. Now, because it is so much easier to visualize,
what is it?
Is basically casting shadows with a beam of electrons. You're shooting a high energy beam of electrons all the way
through. Okay, so we're shooting a high beam, a high energy. High energy? What do you mean? Electrons have energy?
An electron microscope is basically casting shadows with a beam of electrons. You're shooting a high energy beam of electrons all the way through a material, and you're projecting whatever gets through out onto a screen and looking at that image. Now, because it is so much easier to visualize this when you don't use electrons, I'm going to be doing a demonstration with photons. If I have a point source of light, like this flashlight with a piece of poster board with a pinhole in it, any shape that I put in front of the light casts a shadow on this screen. And critically, the shadow is actually magnified based on the relative distances between the source, object, and screen. Huge wrench. Small wrench. Big wrench. Small wrench. I need to get out more. But if you notice, the edges of the shadow are a little bit fuzzy. If we try to look at something really tiny, let's say these ball bearings are like atoms being imaged in a microscope, this method doesn't really let us see anything. One of the multiple problems here is that the pinhole isn't actually a very good point source. It's almost the same size as the features that we're trying to image. So light from one edge of the pinhole and light from the other edge of the pinhole actually cast very slightly different overlapping shadows. And in order to accurately image the atoms then, all our electrons would need to originate from a point in space that's smaller than an atom. And we can't do that. If we're slightly more clever, we can use lenses to project a sharp image, even with a less than perfect source of light. Here, I set a lens so that as light exits this pinhole, it's actually made into a nearly parallel beam. That parallel beam passes through the ball bearings and a shadow is created. And then we can take that beam, and if everything is lined up just right, blow it up to project a larger shadow on the screen. Once we send it through here, it gets smaller, comes down to a point, and then way blows up and expands out here. So we have a magnified image on the screen. Remarkably sharp. Much better than I thought I'd get with this. Those are our atoms. Just imagine that instead of a flashlight with a pinhole, we have an electron gun powered by a huge high voltage power supply. And instead of glass lenses, we have really big electromagnets that bend that beam of electrons as it's passing through the microscope. Now, compared to our flashlight model, the electron gun is at the top of this system. And it's focused by a series of magnetic lenses capable of bending the electron beam onto the sample, and then through the sample, and then through more lenses that expand that image into a camera. Now, when we turn this whole shebang on, we literally just get a shadow image of the copper crescent. Pretty cool, right? Yeah, so here you can really see that the place where there is nothing, like this, you can just see bright because that's where the electrons are hitting uninhibited. This thing is the big chunk of copper that the electrons can't get through, so it looks black. And this is the sample, which is so thin that it's electron transparent, and it actually sort of looks gray because it'll let some electrons through, which is kind of the point. You can see huge bits of strain and bending in the sample as it's sort of warping around. It's really interesting. But right now, what we need to do is basically get the beam pointed at the sample and get the sample pointed at the beam. Getting the beam pointed at the sample sounds pretty straightforward, but getting the sample pointed at the beam, that's a weirder phrase. You need to remember that we're dealing with a crystal, this perfect 3D grid of atoms in space. Now, earlier I used a ball bearing to emulate a single layer of atoms, but what if I had 2 layers, or 3 layers, or 10 layers? It gets a lot harder to tilt the sample, so you can look straight down a column of atoms. This is another reason that we like to keep the samples really super thin. The sample looks a lot different now because we're actually focused on it, which is, the first step. The next step is to get the sample tilted so that it's actually pointed at us. The sample need not load in perfectly flat with respect to the beam. The good news is that we can use the electrons passing through the sample and making diffraction patterns to actually help us line this up. We've got this awesome starburst pattern called a Kikuchi pattern. We basically just want to line this up so that we're looking at the center of this starburst, which is called the zone axis. Make it look real starbursty? Not really. The sample might be a little thin for that. So I hope that explanation made sense. So I'm about to rip the rug out from underneath it. While it's possible to image atomic scale features using this very technique where you're basically casting shadows of atoms, all of these extra fringes and patterns sometimes make...
Okay, it doesn't matter. This is just technique to see atoms. It's very nice, but it's atoms. I don't know. I mean, atoms are electrons.
Atoms are electrons.
I mean, when you look at an atom, you're seeing the electron cloud.
Oh, okay.
Alright,
so I gotta go.
You gotta go?
Yeah.
Okay.
Alright. See ya.
Wait, Science Asylum replied to one of my comments.
Really?
So I said in one of his videos, even a single pendulum is difficult if theta is not small. And he said that is true.
What video? What was that about?
It's a video about
Thanks to Brilliant.org for sponsoring this episode.
Lagrangian mechanics. Are you familiar with Lagrangian mechanics?
Not so much.
It's the least action.
Oh.
Wait, let me see if he shows the graph. It's I don't think I've ever. I mean, maybe I did it many years ago. I wouldn't even. I think I did because I think I did like. I took advanced mechanics. This is it. So the action is the integral of all the Lagrangians, and you want to minimize. You want to minimize the action. You're looking anyway. It's the Lagrangian is the difference between the potential, and the Lagrangian is just the difference between the kinetic and the potential energy.
I see. So you want to minimize that.
So the way I see it, it's like if you're trying to solve any mechanical problem, any advanced mechanical problem, like a double pendulum or something. So really, you're asking the system at any given point in time, what are you going to do next? How does the double pendulum know what to do next? So the answer is it's going to always minimize this quantity. That's the idea. It's always going to take the next delta kinetic energy minus the delta potential energy and minimize that. Like, how does a stream of water know to take a path, a certain
delta
path?
Or integration?
I think, yeah, but it's the integral. But how does the system know, right? The system has to choose. It's basically, I would say, it's a greedy algorithm. Like the universe, this is supposed to say the universe is lazy. The universe is trying to do the least. This is the least action, or the least. It's also called the least effort. So you're trying to you take the integral of the action. The action is what we saw. The action is the difference is kinetic minus potential. Sorry, the action is the Lagrangian. The Lagrangian is the kinetic minus potential. And you're integrating, but the question is, anyway, I've never used
so the
it.
variation of the action equals to 0 is the optimal point.
Right.
That makes sense. So it's actually the derivative of that integral.
Yes.
Yeah.
So you're taking the action. This is a function. It's some function.
So for the previous one, it's like the change in kinetic and the change in potential energy is 0. Yeah.
The idea is that, let me see. The idea is that there is an optimal path, right? You're asking the least action philosophy, the least the principle. It's supposed to give you the true path that the universe will select. So you're throwing a rock, let's say, under some very complicated gravitational influence, and you're asking, okay, it's going to start here. Where will it end? What path will it take? How much time will it take? And you want all the information. So you're feeding it. But basically what you're saying is, let's assume this is the answer. Now let's make a tiny modification. Let's perturb the system a little bit. And it should give you a bigger action. That is not the minimal. If this is the true answer, then this is the minimal effort. And the universe always does the minimal that it can do. That's the philosophy. There is a mathematical proof. I've never seen the proof. So, but that is. So I was watching his video, and interesting that he responded. This is from 5 years ago. Anyway, you have to go?
Yeah, I have to go.
All right, man. Thank you very much for joining me. All right. Okay, I think we're done. I have to think about this. This is. Yeah, let's stop here.